Okay, can you see my screen?
Yes.
Okay. Okay. Good morning, everyone. So today I'm going to talk about data flow hardware acceleration of DNNs with high-level synthesis. We'll start with a brief introduction, and then I will talk about our first work, FlexCNN, an end-to-end framework for composing CNN accelerators on FPGA. And next, I'll talk about Stream-HLS towards automatic data flow acceleration. It was just accepted to FPGA 25. So there are some challenges with the traditional computing. First, as we all know, Moore's law has been slowing down due to the physical limits of how small transistors can be and other physical limits. And general purpose computers like CPUs and GPUs usually sacrifice efficiency and performance for generality and flexibility. We can see that the breakdown of an instruction energy, that most of the energy is consumed on memory accesses, control logic, and only a small portion on the actual arithmetic operation. Also, we see a trend that you can have an order of magnitude better energy efficiency when you move from CPUs to GPUs and then to general purpose DSPs and then to dedicated hardware like ASICs. So the third challenge is also the rise of compute and memory hungry AI algorithms. This made the matters worse. And the solution to this has been to focus on customization and domain-specific hardware on the level of the architecture itself. Some of these examples include the Google TPUs. These are built as systolic arrays on ASIC. Cerebrus wafer scale engine, also an ASIC. And also Microsoft Brainwave project, which built cloud infrastructure using FPGAs to accelerate their workloads. So there are generally two types of hardware architectures. One is the von Neumann architecture, and the other one is data flow architectures. For the von Neumann architecture, it's basically a load, compute, store architecture. It has sequential nature because it will execute instructions sequentially. And then it has a shared memory for instructions and data. It has a program counter to direct the execution flow. And it's limited due to its inconcurrency due to its sequential nature. Something like this. This will include CPUs and also GPUs. And then there's another type of architecture called data flow architectures. The execution model is more parallel execution based on the availability of data. So it basically tries to match the actual computation graphs where data will flow through this computation, but we realize it in hardware. And data dependencies will dictate the computation because nodes that do not have their data ready will have to wait for previous nodes. And the control flow is triggered by the data readiness and availability on data between the nodes. And it naturally have high concurrency. And this is an example of a data flow accelerator. So first, I'll start with FlexCNN. This architecture is a hybrid von Neumann data flow approach. So what I mean by that is, I will talk about this in a second, but basically we have a data flow architecture that within the execution of this architecture, it's a data flow architecture, but this architecture will be called multiple times using load, compute, store style. So first, I'll talk about some challenges with modern CNNs. The first challenge is the computation to communication ratio disparity within CNN layers of the same type. The second one is handling various types of CNN layers, especially, for example, transpose convolution and dialectic convolutions. I will talk about these also in this slide. And the third one is end-to-end integration with machine learning frameworks. So as I mentioned, FlexCNN is this Dataflow accelerator. It uses a runtime configurable and composable streaming Dataflow architecture to implement a specific CNN. What we mean by that is we have this architecture which have multiple hardware modules that are connected with streaming channels or FIFOs, first in, first out queues, you can think of it. And then here we will load the data from off-chip memory or DDR, and then do the computation and store the data to the DDR. So to like realize or implement a specific CNN, we will invoke this architecture multiple times. That's where the von Neumann Dataflow architecture hybrid comes in. And it has multiple modules. These with two gray lines, these are line buffer-based architectures to keep the data flowing. And then for the convolution operation, we have a versatile systolic array architecture. So for the disparity of CNN layers of the same type, what we mean by that is, you know, in like many CNNs, you start with a large height and width of input feature maps, but maybe shallow number of input channels and output channels. And then as you go to the next layers of DNN, the height and depth, the height and width of the CNN features will get smaller, and then the channels may get wider. So this leads to different computation to communication ratios in these different layers. And to address this issue, we developed a dynamic tiling and data layout optimization. Basically, if we have fixed tiling factors for all the layers, then we may have this type of execution for a set of tiling factors, number one, where the pipeline is bottlenecked by either reading the data from off-chip memory or writing the data to off-chip memory. But if we use another set of tiling factors, we can basically balance the computation and communication stages of the computation. And this is shown with this tiling factor number 2. And this figure shows the performance comparison using uniform, like same tiling factors and dynamic tiling factors that we configure during runtime for the first 24 layers of CNN called OpenPose that estimates the human pose. So we can see that with this all uniform, we get around 24 gigaflops. But when we change to all dynamic tiling factors, we can reach up to 149 gigaflops, which is a 6x increase. And here are the performance of each layer. The second challenge is handling various types of CNN layers. So, for example, this is a network called ENET, small neural network used for segmentation. It has many types of convolution layers. It has a total of 209 DNN layers, 78 normal convolution layers, 8 dilated convolution. I will also discuss what these are, and 3 transposed convolution layers. And the basic block of this CNN looks like this, where you may have either like the normal convolution or dilated convolution or transposed convolution. And here we see that, for example, the first modules are just downsampling, and then we have a bunch of normal convolution layers. And then we have these upsampling layers, which is this transposed convolution, and so on. So since we have all these types of CNN layers, how would we create the hardware for them? And since we are reusing the same hardware. So our approach is so there are two types. We classified the types of CNN layers into two types. One is compute intensive layers, which comprise normal, transpose, and dilated convolution layers, and then non-compute intensive layers like pooling, upsampling, activation, and batch normalization. Our solution is we create a dedicated hardware called a versatile systolic array for these compute intensive layers, and then we create dedicated hardware for the non-compute intensive layers. And this is an example of the architecture where we have this versatile systolic array for all types of convolution. It's a big systolic array. And then we create the other modules since they don't take much area and hardware resources. And the versatile systolic array is basically instead of creating one hardware for normal convolution, one hardware for transpose convolution, and one for dilated convolution, we combine them all in one thing, like runtime configurable systolic array. So here I'm gonna talk about what this is, the transpose convolution, also called fractionally strided convolution. It's basically an upsampling layer that uses trained weights to produce high resolution feature maps. And if we try to naively implement this layer as a normal convolution, we will insert zeros in the input feature maps as shown in this picture. And then we run the normal convolution algorithm on it. So we will start with the sliding window of the kernel at this position. We move here and so on. But you see that we have a lot of zero multiplication operations, which will lead to huge underutilization of the computation resources due to these redundant zeros. And then for dilated convolution, or also called Atraus convolution, it maintains the resolution and coverage of the feature maps by expanding the receptive field of the convolution filters. And both of these types of layers are used in image segmentation and it also, for this dilated convolution, instead of inserting zeros in the input feature maps, we will insert zeros in the kernels to increase the receptive field. So instead of so this is a 2x2 kernel, but when we insert these zeros, it will be increased to be like a 3x3. But again, we have all these zeros that will lead to huge underutilization of hardware resources. So an efficient implementation of transpose convolution will decompose the filters, converting the problem into normal convolution. So basically, we'll have this algorithm decomposed into a set of these operations. So if you notice, for example, at the first, if we do the normal algorithm, when we take the filter or the kernel and apply it here, only the four corners are activated. So it'll be the 9, 7, 3, and 1. At the next spot, it'll be just top and bottom. The third spot will be again 9, 7, 3, and 1. And when we go down to this location, it'll be the left and right. So it'll be 6 and 4. And when we go to this location, it'll be just the one in the middle. So basically what we are doing in this algorithm is we are decomposing the problem into these four patterns that will repeat all over the computation. And now we will do these four dense convolution operations without needing to add the redundant zeros. And this ideally leads to S squared speed up, where S is the it's called the stride for transposed convolution, which means the number of zeros inserted between the rows and columns of the dense input feature maps. Similarly, for dilated convolution, we will insert these zeros in the kernel, and to decompose it, we will decompose the input feature maps in a similar approach. So we will have certain patterns, and we will decompose them into these dense feature maps. And this also leads to the speed up calculated by where D is the dilation factor, also means how many zeros you insert. And instead of, as I said, creating 3 different systolic arrays for each one, now that we have this decomposition algorithm where we can turn them all into normal convolution operation, we can add hardware signals to specify which type of convolution we are running, and we pack them all into one versatile systolic array as shown in this figure. And we have the initial evaluation results on this versatile systolic array. We can see that the blue line is the ideal speedup calculated by the formulas I just showed. Sorry. For communication bound layers, we may not reach this ideal speedup, but as we reach to computation bound layers, we can almost have the same as the ideal speedup. And in terms of resource utilization, we see that this versatile systolic array doesn't add much hardware resource penalty. It's just around 7% in terms of LUTs, 3% in terms of flip-flops, 3% for DSPs. And for memory, we see that here we are using more URAMs, here it's less, and here we are using more BRAMs, and here it's less. So kind of balance each other out. The last challenge is the end-to-end integration with machine learning frameworks. So we know that the overhead, the convolution is the main, one of the main bottlenecks, but also when you run end-to-end applications, you may have other overheads, for example, the other operations, loading the data to the FPGA and other things, and these are usually overlooked. So what we did is we proposed a 2-level pipelining approach where we have the software level pipelining, where we pipeline the CPU processing, like pre-processing of the images, with the FPGA inference. And the other hardware level pipelining is we overlap DRAM or off-chip memory read and write with the kernel invocation. And these two lead to 2x speed up for the first level pipeline, and then further 5x speed up for the hardware level pipelining. And our framework starts with the ONNX format, and it can take, so multiple CNN models can be converted into ONNX. We start with a template of the modules that will be utilized in the architecture. And then in this CNN layer, mapping will basically try to map the CNN layers into this template that we just created. And then we will run design space exploration to find the optimal tiling factors that we mentioned that are dynamically determined. And we will generate the instructions to control each invocation of the accelerator. So also we have, I didn't mention here, but data layout optimization. This maximizes the off-chip memory burst length so that we can maximize the bandwidth of off-chip memory. And for the design space exploration, all hardware modules in FlexCNN are parameterizable. So we need to determine the size of the systolic array, for example, the on-chip memory resources, etc. And we also built an analytical performance model to estimate the performance and resource utilization. We start by exhaustive search of all possible hardware parameters. And then for each set of hardware parameters, we do a greedy search to find the best dynamic tiling factors for each layer. And here are more results on the versatile systolic array. Again, when we have small convolutional layers, we cannot achieve the maximum efficiency of the systolic array. But as we reach to more and more computational intensive layers, we reach close to the ideal hardware utilization for both transpose and dialectic convolution. And then for the overall performance, we tested 3 neural networks. One was the OpenPose, compared it with CPU and GPU. We can see we are slightly faster in terms of latency and throughput than GPUs, and also faster than CPUs. And for UNet, it has these transpose convolution layers. It's used in medical image segmentation. We can see we have better performance than GPUs. And also, when we compare with prior works, this work is performing better because it's using 8-bit type, while we are using float 32-bit. And we are also competing or better than this fixed 16-bit. And then for the ENet, we compared with also CPU and GPU, and we have better performance than both of them. And we also compared with Xilinx DPUs. These are hardware RTL optimized modules. We can have some competitive performance with the this light version of this architecture, and also competitive performance in terms of latency with the large one. Okay, now I'm going to talk about Stream-HLS. This is more of a pure data flow approach. So basically, there are in my opinion, two key factors limiting wider adoption of data flow accelerators. One is the difficulty of automating hardware design. Basically, how to automatically implement a given or known design point as a data flow accelerator. And the other one is the complexity of exploring huge design spaces, or how to find a good design point. Many prior works have tackled these challenges, yet significant issues remain unresolved. The first type of works in HLS tries to insert pragmas into the code to explore the trade-offs of different pragma combinations. And these prior works include HARP, also from our lab, and O2DSE and MLP-DSE. However, this approach does not explore the space of code and loop transformation opportunities, which affects the quality of the code in a big way. And then there are other frameworks that target a single kernel, like a single layer of a DNN, or a single general matrix multiplication operation, or a single stencil operation. This includes O2SA and SODA. They do code transformation and design space exploration, but as I mentioned, they are limited to a single kernel application. And there are other abstraction frameworks like Allo and HeteroCL. These provide more of a higher level abstraction to design hardware accelerators by decoupling algorithms from hardware scheduling optimizations, but they still require manual design space exploration and manual design of these accelerators. And last type is multi-kernel frameworks like Scale-HLS, HIDA, and PALM. These frameworks, they apply code transformation and design space exploration for multi-kernel applications. Multi-kernel applications, for example, a CNN or multi-layer perceptron or any other application consisting of more than one kernel. But these frameworks do not really implement Dataflow architectures, so they are lacking streaming capabilities or have limited DSP. So our framework Stream-HLS falls under this fourth category, but produces globally optimized Dataflow designs with streaming capabilities and uses mixed integer nonlinear programming design space exploration. So Stream-HLS is a hardware MLIR-based compiler that takes a sequential multi-kernel application and automatically converts it into a parallelized Dataflow architecture. If you're not familiar with MLIR, it's basically an extension of LLVM compiler infrastructure that allows you to create your custom types and operations in a group, and you group them in what is called a dialect. So our framework is built on top of this MLIR infrastructure. And it's been used in many custom and domain-specific compilers. So let's start with this motivating example. 3MM is basically this application where you have three matrix multiplication operations where the first two are input to the third one. And this application is from a fully benchmark. So this is the core code of this algorithm. We will have the first two matrix multiplications send the data to the third one. And this is the architecture that we will generate with Stream-HLS that will let these three operations communicate with FIFOs. For such multi-kernel applications, we identify three critical but often conflicting optimizations that will determine the overall performance. And in this case, so in the previous FlexCNN, we had one accelerator, for example, one gem accelerator. We will run it 3 times. That's why we call it von Neumann Dataflow hybrid. But in this case, we will actually implement each of the operation on chip, and there's no external control. It's just you invoke the kernel, it will read the data and process everything and send it out. I will mention later some limitations of this approach. So the 3 points that determine the overall performance is node level pipelining. So this means the pipelining within each node of the application. Graph level pipelining is the pipelining between the nodes. And then node level parallelization is the level of parallelism within each node. So in your HLS class, I think you've learned about the Pragma HLS pipeline. So the code on the left, we have this reduction loop in the innermost. And if we try to put HLS pipeline here, we will have a small distance for the loop carry dependency, and we will not be able to achieve II1 because we are accumulating to the same memory in executive iterations. But we can solve this issue by doing loop permutation, where we put this reduction loop outermost, for example. Also, the latency here would be around 4 times this number of trip counts. But if we did this loop permutation, we can now achieve II1, leading to around 260K cycles. This gives us around 4x speed up. However, now if we look at the same problem, but from the graph level, the loop permutation also impacts the degree of concurrency between dependent nodes. So even though that this one achieves an II of 4, we know that the first output, or this temp 100, will be ready after around 127 iterations of this whole loop nest. But when we did the loop permutation, even though we will have II1, the first output will only be ready after 260K iterations. So this indicates that a node consuming this temp1 must wait until the first output is ready. Here, the first output is ready after 127 iterations. Here, it's after 260,000 iterations. And this is demonstrated in this figure. So first, if we don't use any FIFOs, they will have this gem3 because it depends on the first two. It will have to execute sequentially. And then if we change some of the loop permutations and we use FIFOs, we may get this overlap, maybe similar to this 260K iterations. But if we searched all possible loop permutations, we found that this is a better option where you can almost overlap the whole execution of the three operations. And the design space for just the loop permutations in this example will be 3 factorial for the 3 permutations of the first node times the second one times the third one. We have 216 different schedules. And now we talk about node level prioritization. So far we've been assuming that you have a single operation at a time. But now to increase parallelism within each node, we employ tiling with loop and rolling. But how we will choose a good tiling and parallelization factors and how to guarantee that you can still overlap the communication computation between these dependent nodes. So in this example, let's say we have 3 nodes have different number of operations or like trip counts, like 2 million, 4 million, 3 million. The first approach would be just to use uniform parallelization, for example, parallel factor 2, meaning we dedicate to a compute units for each loop nest. This will cut the time by 2, but since this work is unbalanced, this workload is unbalanced, we will have this execution. Now, a better approach would be adaptive parallelization, which means we will dedicate the computational resources according to the computational intensity of each layer. And this will be better. But now when we consider also the loop permutation and how they affect the overlap between computations, we see that this is the best schedule. And this is what Stream-HLS finds. And the tiling and parallelization design space for this problem with this problem size is around 331 designs. And under only these 3 optimizations, the design space becomes 216 points times this, around 71 million designs. And given only these 3 optimizations, 3 challenges arise. One is how to automate streaming capabilities with FIFOs. Second is performance modeling, how to estimate the performance of a given data flow. And then how to explore this design space. So first, I'll talk about streaming automation or how to legally replace a shared buffer with a FIFO. For this, 2 conditions must hold. First, the number of writes to a shared buffer must equal the number of reads, and then the order of writes must equal the number of reads. And I have these compiler passes and MLIR that will automate this. So we'll start with the pre-processing pass. So in HLS, before you can synthesize the design as a data flow design, there are some conditions that must be met. First is every buffer must have a single producer, single consumer relationship. So for example, this case, on the left, we have 2 reads to this C buffer and 1 write. So this does not satisfy the single producer, single consumer relationship. And also the number of reads does not equal the number of writes. Here we are writing 32 cubed times, and then here we are reading 32 squared times. So this condition is not satisfied. So this first pass will convert the design into this format, where we create local buffers and we only, which will be reused across the iterations of the first node, and we will only access it at the beginning of this operation and at the end. And now, if we look at this shared buffer 2, it has a single read and a single write. And the number of writes equals the number of reads because this if condition. So first condition is satisfied. Next is the shared buffer to FIFO conversion. So this pass will check the access patterns of the read and writes. If you look at this example, we have, with respect to the indices of this buffer, this is accessed in the order ij, while this one is accessed in the order ji. So the write access function does not equal the read access function, and the second condition is not met. So the pattern in this example are not equal, so the shared buffer will be maintained. However, fortunately, these access patterns can be equalized through loop permutation that we just discussed. So if we just permuted these two loops, now the first condition is already satisfied from the previous step, and now the write access function equals the read access function, and the second condition is satisfied. Now we can safely replace this shared buffer with a FIFO. And this will ensure that this operation can start before this operation ends. And this takes us to the next step, which is the code transformations and design space exploration. So there are optional passes plugged between these two passes that I just mentioned, which will create a performance model to use as the objective function to search for good design parameters. And then the design space exploration that will use mixed integer nonlinear programming. For performance modeling, we create a Dataflow graph, which is basically a directed acyclic graph, where a node represents a perfect loop nest, representing a high-level operation like matrix multiplication or convolution. And then an edge is a read after write dependency. And then the DAG is sorted topologically, and we construct a closed form formula to estimate the performance of this design point and their specific parameters. More details about the performance modeling is in the paper. And then we use this performance model that we have this closed form formula to estimate the latency of Dataflow design point. We will use it as an objective for a mixed integer nonlinear program. And we constructed 3 types of these programs. One is we handle graph and node level pipelining, which is only affected by the loop permutations. So for this case, we use d factorial binary variables per node. And don't worry, the number d here will be small, just the depth of the loop nest, which is maximum like 6 for convolution. This will find the best loop permutations of each node. And then we have a node level parallelization program, which have d integer variables per node. This will determine the tiling factors of each level of the loop nest of a node. And then we have a combined optimization, which will try to combine these two into one big mixed integer nonlinear program. The reason we split them like this is this combined optimization, when we add both the binary and integer variables, may not be scalable. But if we solve them in 2 steps, this can be this may not give us the optimal solution, but it's more scalable. So for the evaluation, we tested it on 7 small multi-kernel applications from the Polybench benchmark on 2 relatively small multi-layer perceptrons, 2 transformer blocks, and 2 CNN blocks, and also 2 synthetic applications. We used medium problem sizes to reduce RTL simulation times, and we used Vivado and Vitis HLS 2023.2, targeting AMD U280 accelerator card. And we conducted 5 sets of experiments. One is just the automation part, where we just convert shared buffers whenever possible to FIFOs. We don't do any code transformation. The second one is we perform graph and node level pipelining only. And third is we convert the shared buffers to FIFOs, and we don't do loop permutation. We do just loop node level parallelization. And then after 4, we will do the 2 steps, but in separate mathematical programs. And the last one is we will do them with the combined performance model. First, we did the performance model validation. We tested with the opt1 designs and also opt5. Opt1 because they will feature like various like behaviors of the original programs, and we see that we achieve 99% of the actual performance compared to even better than Vitis HLS estimates. Vitis HLS estimates for Dataflow designs is usually not accurate because it cannot determine the level of concurrency between dependent nodes. And then when we add all the optimizations and the parallelization, our estimations drop a little bit, but it's also comparable to Vitis HLS. And then first, we compared with the prior manually optimized works that I mentioned, Allo and HeteroCL, that gives you a high level of abstraction. So for these designs, they were manually optimized using their scheduling languages. And then we also compared with automatically optimized frameworks, IDES, KLHRS, and POM, and also with the naive Vitis HLS designs without doing any optimizations or data flow optimizations. So we can see that, and this is the latency in cycles in log scale, where we can see we always almost like have better performance than all prior works, thanks to the overlapping between the nodes and the maximization of the distribution of the computation resources equally between nodes of different computational intensity. And we also outperform even the manually optimized designs by 3 and 6x speedups, both because of the scheduling of Stream-HLS and also using the streaming data flow designs. And here is the 3mm example we showed earlier. So, for example, this figure on the right is what HIDA finds. You see that there is no overlap between dependent nodes because it doesn't use streaming. And also even computational resources distribution is not balanced. And for Stream-HLS, this is the design we have where they have almost uniform or same execution times and also fully overlapped. Also compared with another work, we see the same pattern for the smaller budget of DSPs, and ours is slightly better. And also this impacts the DSP efficiency of our designs. We reach up to 92% compared to 65% for HIDA because some of the hardware resources will not be utilized, for example, in this step, and also 83 compared to 60%. And also we did some ablation studies to see the impact of each optimization. So for the shared buffers to FIFOs only, this is the baseline. And then when we do just the node and level graph and node level pipelining, we're just consider loop permutations and maximizing the currency without parallelization in any nodes, we gain 4x. And then if we just did node level parallelization, we gain 28x. And then if we did op2, then op3, solve them in separate ways, we get 152x speed up. And as I mentioned, if we did the combined optimization, we will have the best performance. Yeah, in conclusion, with the slowdown of Moore's law, custom and domain-specific architectures have become essential for sustaining performance and efficiency. Dataflow designs have demonstrated strong effectiveness in addressing the computation and memory challenges of modern AI workloads. And in this talk, I presented two complementary approaches, FlexCNN, which is a hybrid von Neumann Dataflow approach, and Stream-HLS, which is a pure Dataflow compiler. So together these works show a pathway towards scalable, automated, high-performance domain-specific computing. And here are the links to our projects if you are interested. And I'm ready for any questions.
Thank you, Suhail. So, any question? I have a question. Sure. Can you come to the end?
Hi.
Hi.
So my question is, how do you go about finding good problems to be accelerated by FPGAs, where you could really see a benefit compared to CPU and or GPU? Or is it the case that for most specialized tasks, there is some way you can accelerate it with an FPGA?
I think in general, like the trade-off, I think comes like if you think about any algorithm, it's basically you can think of it as a big abstract computational graph. And if we do it on CPU or GPU, this graph may not be easily scheduled on these architectures, and also due to their sequential nature. But if you customize the hardware as close as possible to the actual computational graph, you will usually get huge performance benefits. This includes DNNs or, for example, Linghao made an accelerator for sparse matrix vector multiplication and sparse matrix multiplication. And by carefully handling all these computational graphs in an efficient way, you can always gain an advantage. Nowadays, I think with GPUs, with their huge parallelism, sometimes they make FPGAs look less useful. But I think for many applications that are irregular and highly dynamic in nature, I think FPGAs can still be competitive, especially if you customize your designs for these applications.
Thank you.
Yeah, actually, I have a few comments. I think this is a very great question because now our computing systems become more heterogeneous because like many years ago, there's only CPUs, but now there are CPUs, GPUs, FPGAs, and
NPUs.
Yeah, from APU, BPU, CPU till VPU. Yes, all those heterogeneous computing platforms. So I think it's very important to understand the characteristics of all those, computing resources that is from the APU to ZPUs, and also understand the characteristics of the applications. And by this way, we can choose the best, platform for our application.
Yeah. I agree.
Any other question? So I have two questions. So yeah.
Go ahead.
So for your Stream-HLS, so you are doing for this conversion from shared buffer to FIFOs, you need to perform loop permutation for the second kernels, right? So my question is that because sometimes after you perform the permutation, probably you are not able to achieve like I equal to 1. So how do you handle this conflict?
So in my performance model, so for example, if you have two nodes and we will kind of like enumerate all possible permutations and we assign the potential or achievable II for each permutation of each one. And then we also have variables to know if these permutations are compatible or not to use FIFOs if they have the same order. So there are these two variables that will how to say, like maybe for some cases the II is more important. For other cases, the overlap would be more important. And solving the performance model with the mixed integer and nonlinear programs will determine what is the best combination of these two. Yeah.
So another question is that so when you are doing the performance comparison for the FlexCNN, you have done the experiment on both U280 and U55 U250, right?
Yeah.
I noticed that there's a network that can you go to that slide? There's a table about the
Yeah.
this slide. So I find that so for ENet, actually the latency of the on U250 is actually smaller than U280, right? But for the U250 you are using floating point FP32, but for U250 you are using fixed 8 point, right?
Yeah.
Do you have any comments? Because I'm thinking that by using lower bit, actually you should have lower latency, but now the latency is higher from 21 to 56, right?
Yeah, that's a good observation. Let me try to remember because I did these experiments a long time ago. Maybe I think
probably there's
I think it's due maybe to the so these two designs are probably not identical. So because we consider the type of FPGA we are using, and then we run the design space exploration to find the hardware parameters. So probably the design parameters for the U250 was different from the U280, and this is why.
Yeah, I agree. Yeah, because
but that makes sense. Yeah, I think I will look into it.
Yeah, just as you said, probably that because for U250 there are more like DSPs, but the bandwidth is lower than U280.
Yeah.
So that your searching engine probably will get some some designs that is better for FP32, but for the fixed 8 point that could be searched to, like, for example, maximize the bandwidth or some other.
Yeah.
All right. Do you have another question from audience?
Hey, thanks a lot for the talk. I had one question with your comparison with GPUs. GPUs have a very high have a HBM with very high bandwidth, and but that's not the case with FPGA. So how did you exactly come up with these numbers when you are comparing? Was it like, how did you come up with the apple to apple
So,
comparison between these two?
okay, so for the GPU experiments, I think, I don't know if this A100 has the HBM. Do you know, Linghao? Because these experiments were in
It's around
2022,
1.5 TB per second.
Yeah.
Yeah, so I didn't check the exact details, but we just had this A100 on our cluster, and we tried to run the inference on both our CPU and GPU uh, uh, kernel, but it's expected to have better uh, results for ENet and UNet, even with HBM, because of these redundant zeros that I just mentioned, which are not existent for our accelerator. And another thing is, for example, for U280, it also has this HBM channels.
So I think actually, because these are the comparison between two platforms, that is GPU and CPU. So it's
It's
GPU
hard to,
FPGAs. So it's very hard, or I would say it's almost impossible to do apple-to-apple comparison, because you are running on GPUs or the CUDA code, but
So was there any scaling involved? Because the operating frequency of the GPU
it's
and
also higher than
so it should ideally the throughput should be
yeah, but here remember that for the FlexCNN framework, it's an end-to-end, acceleration framework. So what you need to, for the comparison, what you need to do is that you just take a model from like the Onyx on the platform, and then
and also
end-to-end performance.
And also, just to point, like, so we know that GPUs and CPUs, you see, like, they can run at much higher frequency, but what we argue for custom and domain-specific computing is when you customize your architecture. So when you have this generality and flexibility of GPUs, you will always lose on some performance and power efficiency, etc. But when you customize your design for the specific application, even if you run at 10% of the frequency, you still can compete because of this customization, compete in terms of performance and also in terms of energy efficiency.
Okay, thank you.
One more question.
Yep.
Hi, Suhai.
Hi.
Thank you so much for the talk.
You're welcome.
So I have one quick question about the it's actually maybe slightly off the topic, but I want to ask, like, what are some like actual like application scenarios for like CNN or deep learning model acceleration on FPGAs? Because like I want to ask this because, for example, on a robotic example where you probably want to do like image recognition using like inference chips and things. So if the algorithm you want to run is very general, you want to use it in a lot of places, like why not just buy some like general chips or ASICs that are already taped out and been made suitable for CNN inference and deep learning models. And so my question was like, what is the actual application of FPGA inference and what are some of these application scenarios?
Okay, if I understand correctly, like there are some ASIC chips that are designed for like CNNs and DNN acceleration. Is this what you're saying? And why would we use FPGAs?
Yes. So yeah, sorry for the confusion. My question was like, why not use like ASICs in that scenarios? And if
yeah, go ahead. So the main advantage of FPGAs is it's like the reprogrammability. So let's say you designed a hardware circuit for some like MobileNet or VGG16, and then 1 or 2 years later, this ENIT came out, and it has different types of layers, so your previous accelerator will not work. If it was an ASIC, then your chip cannot support this new DNN model. But with an FPGA, you can create a new design and pre-program it with this new design. So you have this flexibility. And so you can theoretically create an ASIC or a design that will support, let's say, CNNs only, or you can create one that supports CNNs and transformer models and multi-layer perceptrons. But I think this is just my general idea is the more flexible you make your accelerator is, the more you lose on the performance efficiency
yeah,
and the power efficiency. And the more customized for a specific workload and even a specific like single workload, then the more you can squeeze more performance and energy efficiency in that scenario. But you lose on the flexibility. And if you make it on ASIC, then that's a problem. You cannot like do it on scale.
got it. That makes sense. Could you give me like a quick example where there's a scenario you actually want to constantly change the algorithm and reprogram the FPGA? You know, like, is there any like example of these applications?
I think if like in the past few years with like the main obvious one is machine learning and DNNs because you have like new architectures, new types. First you had like multi-layer perceptrons, then we got CNNs, then recurrent neural networks, then um, uh, LSTM, I think, and then now you have the transformer, but we don't know what's coming next. So it's a very fast changing world in terms of the algorithms and the hardware. One difficulty we face in the domain and customs computing is we need to have some automation frameworks that will keep up with this rapidly changing world of the AI and machine learning. Yeah.
Got it. Thank you so much, Suhail.
You're welcome.
Okay. So I think our time is up. So